Hey, Physics 157. I'm going to do a quick video solution for the freezing lake problem from Homework 3. So, sorry for the bad sound quality. I don't have my mic set up, but I think you should be able to hear me okay. So this is the problem where we've got a lake. It's -10 above the ice, and the water below the ice is 0. And we want to understand how quickly does the ice layer build up, and when are we going to be ready to play hockey? So I usually like to start by drawing a picture of the relevant things in the problem. And so here I've drawn this layer of ice, and that starts out with a thickness of 1 centimeter. And above the ice, the air is -10 degrees Celsius. Below the ice, the water is 0 degrees Celsius. And so this is a situation where I can recognize it as a conduction problem because I have a layer of ice and we've got a temperature difference between the two sides. And so what I expect then is that I'm going to have some heat that will flow through from one side to the other. And then what happens when the heat flows? Well, that's coming out of the water. So the water is at 0 degrees, and when you take heat out of it, then the water is going to freeze. And so then we can figure out, well, how quickly does the water freeze, and then how quickly does ice build up on the bottom? But let's take it one step at a time. The first thing we can do is figure out how much heat is flowing in a certain amount of time. So the question asks, basically, how much ice is added per hour? So how much ice? So we can just try to figure out how much extra ice there will be in 1 hour. Okay. Now, one of the things with this problem is that it doesn't really tell you the area of the lake. But if you think about it, it shouldn't really matter how big the area of the lake is. The rate of freezing would be the same. It should just be determined by the difference in temperature between the outside air and the water under the ice. And so we can basically focus on any area of ice that we want to. So even though we have this big lake, I'm just going to imagine we're going to analyze what's happening in this little area A, part of the lake. And might as well just make it simple and call that area 1 meter squared. Okay, so the ice is going to get thicker under that 1 meter squared just as fast as it will get thicker under some other area of the lake. All right, so the first thing we can do then is to calculate how quickly the heat is flowing from the water out into the air. And that's just using our ordinary conduction formula. So H equals Ka times the hotter temperature minus the colder temperature divided by L, which is the thickness of the ice. And so we're given in this question that K is 2.18 in SI units, and A I'm just taking to be equal to 1. The temperature difference is 10 Kelvin or 10 degrees Celsius, and the length, I'm going to put that into meters so that I'm working in SI units, and then that will give me a heat current in watts. And so if I work that out, then I get 2180 watts. Okay, or 2180 joules per second. So for my 1 meter squared of ice, then I've got this amount of heat that flows every second from the 0 degree water up through the ice and then out into the air. So now we want to know, well, okay, how quickly does that freeze the water? And in particular, like how much extra ice am I going to have in an hour? So to figure that out, well, I know how much energy is flowing out per second. So I can figure out how much total energy comes out of the water in an hour. So that will be a Q value, and we can just use that to figure out the total energy. We multiply the rate of energy coming out, which is H, times the total amount of time, which is an hour. And so if I multiply those things out, so that's 2180 joules per second, times 3,600 seconds. And I can work that out on my calculator, and that works out to be 7.85 times 10 to the 6 joules, okay, in 1 hour. All right, so that's how much energy comes out of the water. Now we want to figure out how much mass of water does that actually freeze. And so obviously this is a situation where, because the water is already at 0, the only thing we are doing is converting it from one phase to the other. And so in terms of what is that Q going to do, it's just basically changing the phase. And so an amount of heat Q taken out of water will be able to change the phase of a certain mass of water, M, and to get that we just use this Q equals ml. So Q equals ml tells us that the mass of water that we are going to freeze by taking that amount of heat out is Q over L, and that works out, if we use the L value for the latent heat of fusion for water, and we divide our Q value for that, that works out to 23.5 kilograms of water frozen in 1 hour. Okay, so we're not quite done, because now we want to figure out that amount of water turns into some amount of ice, and how thick is that amount of ice? Okay, so the thickness is obviously going to be determined by the volume and the area. So we're going to want to convert from this mass of water that is frozen and become ice to the volume of that ice. And so that means that we need to use the density of ice. Okay, so to find the volume, we can use that the density of ice, the definition of density is mass divided by volume. Now we want to find volume, so volume equals the mass over the density. And so if we take that 23.5 kilograms and divide it by the density that's given in the question, then that ends up giving us a volume of 0.0256 meters cubed. Good timing. And so my battery's running low, so let's finish this question. So if that's the volume, and if we assumed that we're talking about just an area of 1 meter squared, well, then it's really easy to find that extra thickness that we add in an hour, delta x. We just have that volume of extra ice is equal to the area of our patch times delta x. And now the area we've chosen to be 1 meter squared, and so we get delta x equals the new volume divided by the area, which is 0.0256 meters cubed divided by our 1 meter squared. So we get 0.0256 meters, and converting that back to centimeters, it's 2.56 centimeters. Okay, so at the start, then we have that we're adding ice at a rate of 2.56 centimeters per hour.